Okay, so what I would like to do in this video is talk about LP spaces. Okay. So basically, this is a way to combine linear algebra, and particularly the theory of normed vector spaces and inner product spaces with integration theory in a practical way that is really the foundation for a lot of data science, the theory of differential equations, et cetera, et cetera. Okay, yeah, so we want to, in particular, form natural norm vector spaces out of integrable functions. So to start off with, I have a definition. So let's say I have a complex valued function f is u plus iv with u v extended real valued functions, measurable. E is a measurable subset. Now let's assume both are finite almost everywhere. Right. So I'm going to define an equivalence relation on such functions f. So we say f is equivalent to g, strictly speaking, on E. So there's a definition. If this is going to be true for almost every x in E. Right? So if f equals g almost everywhere on E, we say f is equivalent to g. Okay. And another definition. All right. Technically, I could do this for p between 0 and 1, but really not going to get into that. That's a little more obscure analysis. So for p between 1 and infinity, and I'll talk about p equals infinity in a little bit, I'm going to define LP of E to be the equivalence class of all such f here, where this integral here is finite. So the first thing to notice is that this condition here is independent of the choice for my class. In particular, if f is equivalent to g, then the two classes are the same. And f equals g almost everywhere, so the integral of absolute value of f to the p is equal to the integral of the absolute value of g to the p. Right. So again, if f is equivalent to g, then the classes are the same. And this integral is going to be the same for the two of them because f equals g almost everywhere. So yeah, this is independent of the class generating, independent of the function generating this class here. And to be clear, so this f so g as before, I just mean we're looking at kind of all functions kind of like this. So if you really want, you could just say g here. So for right. All right. So that means F equals G almost everywhere. So, I guess maybe to be clear, I don't really need this, but this is on E. So, right. All right. Okay, so I'm going to define this norm on LP as follows. And yeah, it's a little wishy-washy to call it a norm, even though, because we haven't proved it's a norm. But anyway. So it's just take absolute value of F to the P, integrate it, and then raise the whole thing to the 1 over P. Okay. Again, this is independent of the representative generating my class, because if F is equivalent to G, then, well, this integral equals the integral of G over E, because F equals G almost everywhere if F is equivalent to G. Okay. So that's pretty clear. And something to be aware of, not just if you're taking the prelim, if you're in my 510A class, but just in general, it's really annoying to keep writing these brackets to indicate a class of functions. So we just don't, and really no one does. I mean, it's kind of it's a matter of, the kind of truth is, if you even forget that LP, the definition of LP is, a collection of equivalence classes, you're basically fine. I mean, if you forgot that, really, you'd be okay until you get up to maybe functional analysis. But even then, it's really, you can almost forget that this is a set of equivalence classes, and you can just think of this as a set of functions, essentially. All right. Okay. So, right, a few facts. So in particular, I'm going to prove essentially, I'm going to almost prove that this defines a norm on LP. The triangle inequality is highly non-trivial, and that's something we'll spend the vast majority of the rest of the video on. Okay, so first, the first property we need of a norm is that this equals 0. And here you got to be a little careful of what the 0 element in LP is. Okay, so this equals 0 implies this is 0. All right, and we proved a few videos back that this means, well, F to the P, absolute value equals 0 almost everywhere on E. Well, that's the same thing as saying the absolute value of F is 0 almost everywhere on E. So it's a little silly to even have the P, but and so that implies, technically speaking, this is the 0 element in LP. Now, what's the 0 element? Well, it's just set of all G where, so stick a 0 here. Kind of obvious, but So remember, two classes are equivalent if and only two classes are equal if and only if I should say, sorry, technically speaking, it's the zero class. So these two are equal if and only if f is equivalent to 0. Well, that just means f equals 0 almost everywhere on E. So f is equivalent to 0. This class is a set of all G, where G is equivalent to 0 on E, and that means, well, stick a 0 here, G of x equals 0 for almost every x. So yeah, this actually is equivalent to f equals 0 in LP. Okay. Okay, so that's the first property of a norm we need. No issue there. 2, if we define this up a bit, whatever. So we're going to define scalar multiplication in kind of the obvious way. So let's say this is some complex number here. So if I define this to be, well, the class of lambda f, you can check this as independent of the function the representative of my equivalence class. All right, then let's do this screen here. Then lambda f So I mean, technically, to be clear, I mean lambda times the class of f. So this is, I'm saying this is the definition. And so this kind of explains why we need the 1 over p. We also need it for the triangle inequality. Absolutely, just to get homogeneity, we need the 1 over p. So here I can pull it out of the integral. So this gives me lambda to the p. I pull it out of the integral. The 1 over p gets rid of this p. So this is just simply kind of trivially lambda times the LP norm lambda times the LP norm of f on. Okay. Yeah. So 3. So I'm going to prove a baby version of the triangle inequality. Right. And so if we define f plus g, if we define the addition of these two classes to be just f plus g, and this is fine. This makes sense, particularly because f and g are both finite almost everywhere. So so there's no infinity minus infinity kind of thing going on, at least almost everywhere. So make that clear. This is defined. And we talked about this before, that when we want to define f plus g on E, we really have no choice but to just look at it for almost every x in E, and kind of just throw our hands up and shrug and say, well, in general, I don't care what this is. It's, or at least off of a set of measure zero. On a set of measure zero, I don't care what f plus g is, as long as it's well defined almost everywhere. And because f and g are finite almost everywhere, f plus g is defined, well defined almost everywhere as a complex number. Yeah, so we did that in a few videos quite a while ago, I think, when we talked about measurable functions. Yeah, and for the purposes of integration, we just don't care how we redefine it on a set of measure zero, because integrating it on a set of measure zero just gives me zero. So at least that's the philosophy. Yeah, and you can check this is, again, well defined. Do that if you want. That'd be a nice little homework. So what do I mean by that? So if f is equivalent to f tilde and g is equivalent to g tilde, then these two are the same. So in particular, the class generated by f is the same thing as the class generated by f tilde, right? A class generated by g is the same thing as a class generated by g tilde. So these two better be the same. Otherwise, well, this definition literally doesn't make sense. But this is the same. And again, this is really easy stuff. Playing around with sets of measures. Okay, so the claim here is the following, easy thing to prove, and that it's the norm of f plus g raised to the p is less than or equal to 2 to the p times LP norm of f plus the LP norm of g. And what's the point? Sorry, I have to raise these to the p. So we would, yeah, so what's the point? I mean, ideally what we would love to have, and it is true, but it's going to be much, as I mentioned, it's going to be much harder to prove. Ideally, we would love to have getting rid of all these p's, getting rid of the 2 to the p. So ideally, we want the triangle inequality. We want the norm of f plus g is less than or equal to the norm of f plus the norm of g. Yeah, it's going to be a whole nother video because that's hard to prove. But the point here is still important, and it's that, yeah, so if f and g are an LP, then so is f plus g. Okay. So yeah, this is going to be really important. F and g are an LP, then f plus g actually also is an LP. Okay. Yeah, why is this true? Well, at least as a complex number, f plus g is defined almost everywhere because both f and g are finite almost everywhere. So they're genuinely complex valued almost everywhere. So for almost every x in E, we have the following. Just by triangle inequality, this is less than or equal to absolute value of f of x plus absolute value g of x, right? And both of these are, well, trivially less than or equal to the max of the absolute value of f of x and g of x. Same thing here. It's gonna be tough to squeeze in, but I think I can squeeze it in. Okay. So one thing I want to point out, you should probably think of this inequality here as kind of the simplest way to prove this fact here. Okay? That f plus g is an LP if f is an LP and g is an LP. That's really the only point of this inequality here. Okay, so that means, well, so these two are less than or equal to the same thing. We're adding two of them. So this is less than or equal to 2 times the max f of x times plus, f of x and g of x. The max, the absolute value of f of x and absolute value of g of x. So this allows me to raise both sides to the p. So if I raise this to the p, it avoids kind of having to deal with kind of like foiling absolute value of f of x plus g of x. I mean, in general, you can't do that unless p is an integer. So that's even more problematic. But yeah, I raise this to the p. If I raise a maximum, let me be clear. I raise a maximum to the p. All that does is takes the maximum of both of these to the p. Check that yourself if you so desire. All right. So let me get rid of this here. Get in my way. Get rid of this. Okay, but this is less than or equal to 2 to the p. Well, the max is going to be less than or equal to absolute value of x to the p plus absolute value of x, so absolute value of g to the p. That's pretty trivial because, well, if the max is this first one here, so let's say the max happens to be this one. Well, this here is less than or equal to this here. It's trivial because I have absolute value of g of x to the p here. On the other hand, if the max happens to be this, well, still this is less than or equal to this because I have an additional absolute value of x to the p here. So the max is one of these two. That's really all there is to it. So now all I have to do is integrate both sides, and that proves exactly what I want. So f plus g, LP of E P, that's going to be equal to this integral here. So raising this to p undoes that 1 over p. Normally, it's going to be this here without the raising it to the p. So raise both sides to the p. It gets rid of this 1 over p. All right. So this inequality right, so sorry, this should be to the p. That's fine. So this is going to be, yeah, this is true for almost every x that we have. This is less than or equal to this. All right, so this is less than or equal to p. times the addition of these two. Right. And again, this is to the p times LP norm to the p. So LP norm G to the p. Yeah, so next I want to prove the trial inequality. And this is called Minkowski's inequality. I'm pretty sure it's not the same Minkowski as in relativity, but that's fine. And so if F and G are in LP, then this is less than or equal to F. So we'll state and prove two important results by themselves. That's Young's inequality, elementary but very clever and useful, and Holder's inequality, which is super, super, super useful. And yeah, I meant to talk about L infinity, but I think I'll do that. I guess I could talk about L infinity real quick. This is getting a little long anyway, so I'll probably make a whole video on doing this because it's not going to be quick. It's not going to be quick at all. So yeah, let's talk about L infinity real quick. Right, so a little definition. M bigger than 0 is an essential upper bound of F on E if the following is true. Well, not surprising. We don't really care about all of E. We just want almost every. We want this inequality to be true for almost every X in E. Okay. Yeah, another definition, or two more. So we say F is essentially bounded on E if such an M bigger than 0 exists. So if there exists an essential upper bound of F on E, then we say F is essentially bounded. So to be clear, we're starting off with an F right here. So complex valued, measurable, finite, almost everywhere. Okay, so another definition. So technically, set of all equivalence classes generated by F such that F is essentially bounded on. Okay, so the norm, and we'll prove it's a norm. So we kind of want the small, I mean, if you kind of think about it, this makes sense. We kind of want the smallest essential upper bound. Um, that's kind of like the kind of maximum of f from our perspective of not caring about sets of measure zero. So that makes sense. That is the infimum of all m, little m bigger than zero. So maybe make this it's actually quicker just to write it like this. Okay, so something that is not trivial at all, but it's pretty easy to prove, is that this is actually a minimum, right? This is really useful. This is like, if you do analysis research, you'll use this, or even data science research, you'll just use this time and time again. This is really, 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 really useful. So the little proposition is that this itself is an essential upper bound of f on E. How do we prove this? Really easy use of just definition of inf. Okay. And I should say, just like before, we're going to stop writing f. Sorry, we're going to stop writing the class f, but really, technically, we really mean this. Yeah, and if m is an essential upper bound for one element in this class, it's an essential upper bound for all elements of this class, because, well, all elements of this class are equal almost everywhere. So, yeah, this is well defined on the class of class generated by f. Okay, so what's the proof here? The proof, well, inf is the greatest lower bound, so this is bigger than infinity. I'm going to stop writing of E because it's, I'm just going to stop writing that. Okay, so that means this here is not a lower bound of this set here. All right. So all we do is look at the definition. And this is a nice little introduction to kind of what you have to do whenever you want to prove things about the L infinity norm or L infinity. It's usually not hard. You just have to, play around with countable unions of sets of measure zero, which we know is still has measures. Okay, so this is not a lower bound of the set. So pick, let's say, mn in the set here. Yeah, I can't copy. That's fine. That. So I'll just write it like this. Oh, easier to write that. Yeah, so this plus 1 over n is bigger than mn. If such an mn did not exist, then this would be a lower bound for everything in this set. Okay. Yeah, if we could not pick such an Mn where this is true, then Mn would be a lower bound. Sorry, this, if such an Mn did not exist, then this would be a lower bound, what I had in yellow. What I have in yellow would be a lower bound of what I have in pink, this set here. What I have in yellow would be a lower bound of what I have in pink if we could not pick Mn where this is true. Okay. Right. So what does that mean? That means that f of x is less than or equal to, this is essential upper bound. So it's essential upper bound. So it's less than or equal to Mn. And Mn is less than this here. For almost every x in E. Yeah, so that means this set here has zero measure. And I'll call this En in a second. And this is just because Mn is less than f L infinity plus 1 over n. All right, so yeah, putting probably way too much detail than I should, but that's fine. Sorry. Technically should be bigger than, but whatever, doesn't matter. So yeah, let's call this En. So let's take the union here. Let's say E prime. Let's say this is going to be the union. So the measure of E prime equals 0. And on X, on E, take away E prime. So if we're not in a union, then, so to be clear, this is, of course, the intersection of E take away En. So this is kind of like the good set here. Well, this is true for every N. Yeah, so take the complement of the union. It's going to be the intersection of the complements. This is true for every N. So this is true for every X. Right, so we have, this is true for on X, on E, take away E prime. So that means F is less than or equal to the infinity norm of F almost everywhere for almost every x. Again, because the measure of E prime is going to be 0. So the measure of E prime is 0, and away from E prime, this is true. Okay. So the set where this is false has to be a subset of E prime. Okay. So yeah, that takes care of the little easy proof here. And let's see. Right. So something to note here. Yeah, so let's just look at this. So it just proved that, well, this is essential upper bound. For almost every x in E. So that implies we have the 0 class. Again, technically, I'm really looking at classes here. So yeah, I want to prove that this is a norm. This is a norm on L infinity. So this is true. So actually, yeah, so actually I forgot absolute values here, but it's not the worst thing in the world, I guess. That's kind of silly, but yeah, well, so you can check very easily if you so desire. If this is a complex number, if it's 0, it's absolutely trivial. Probably just playing around with infimums is the easiest way to do this. Yeah, I would say playing around with infimums is probably the easiest way to do this, but so 3 is the triangle inequality, and this is really easy. Oops. I'm not going to write of E. Sorry, I'm not going to write of E. So this is both true almost everywhere on E. So that implies that so this kind of just illustrates how useful this is. So absolute f plus g is less than or equal to, then add these two norms up. I technically haven't proved that this is a norm yet, but that's okay. Inf is a lower bound of all essential upper bounds of f plus g. This is one essential upper bound of f plus g. So we immediately proved the triangle inequality. So this is an essential upper bound of f plus g. This is the infimum of all such central upper bounds. Yeah, and I'll leave this one as an easy homework for your try. All right, yeah, next up is proving that LP for P between 1 and infinity, excluding infinity, is a normed vector space, and all we need to do is prove the triangle quality. So, yeah. I.e., you have to prove Minkowski's. All right, so long, take care. Bye-bye.